So I lead our carbon services, and I have with me here today, Andres Gutierrez. You can introduce yourself.
Hey everyone, nice to meet you all virtually, and thanks for having us. I'm Andres. I'm also with the Sustainable Building team at Stoke. I have a structural engineering background myself. Spent a couple of years in design, and just recently transitioned over to the sustainability side. So I'm excited to have this presentation today and kind of bridge the gap between both disciplines and kind of showcase what can be done.
Cool. So we'll be talking about addressing embodied carbon. We'll start with a deep dive into what embodied carbon is. We'll go into how that's related to your practice, to structural engineering. We'll spend some time talking about a really exciting new commitment, the SE 2050 commitment, and finalize with some takeaways and Q&A. So first, a little bit about Stoke. So we're an interdisciplinary team of experts focusing on sustainable real estate, from project managers to people with a financial background to structural engineers and environmental scientists. We work to really optimize the built environment for people, planet, as well as profit. So we have offices in San Francisco, San Diego, and Denver. And not only do we try to work on sustainable projects and make projects more sustainable, we're really focused on aligning our intent with our own impact. So we're a certified B Corp, we have a Just label, and we follow organizational biomimicry for our own organizational structure. So jumping into embodied carbon. Over the next 35 years, about 2 trillion square feet of construction is going to be happening. And that's equivalent to an entire New York City every 35 days for 35 years. So that's going to be a lot of new buildings being built. Almost hard to imagine. And it's important when looking at carbon emissions because currently buildings are responsible for 39% of global carbon emissions. And those carbon emissions from buildings are usually broken down in 2 buckets. The first is operational carbon, which is responsible for about 28% of carbon emissions currently. And so operational carbon refers to the energy used throughout a building's life, everything from the HVAC system, lighting, plug loads, and kind of other power throughout the project's life. Embodied carbon, and what we're talking about today, is responsible for about 11% or so of global carbon emissions. And this refers to the life cycle emissions associated with building products. So everything from extracting the raw material, transporting it to factories, the manufacturing, the final transportation to site, any kind of construction emissions associated with that material, and then end of life emissions. So just to illustrate how embodied carbon and operational carbon have been addressed by our industry over time, we can look at one building's carbon profile. So this is looking at a building with conventional, operating conventionally in terms of energy performance. So there's a spike in embodied carbon at the beginning, and then over the life of the building, which we have here is about 50 years, there's a general increase in operational carbon. So there's been a lot of focus on making operations more efficient, better thermal performance, better energy equipment, and this line has really shifted down until we're at this point where, especially in California, it's really feasible to have net zero energy projects. And over time, as renewable energy in the electric grid has increased, that's also pushed down that slope of operational energy. So what you can see is that's really been the focus of the green building movement over the last couple of decades, and that's really left embodied carbon unaddressed. And scientists are really telling us that we need to be looking at a much shorter time frame to have a significant impact, more like 10 to 20 years rather than 50 years that some people are considering. And as you can see here, embodied carbon becomes even more important to consider. In fact, when looking at the global carbon emissions of new construction from now till 2050, about half of those emissions are going to be due to embodied carbon. And it's also important when those emissions are taking place. So there's this concept, time value of carbon. The longer the carbon is in the atmosphere, the more time it has to have damaging effects. So the embodied carbon that mostly occurs before a building is even occupied is there in the atmosphere longer and has a more damaging effect than the carbon that gradually gets released throughout the building's life due to operational energy. So looking a bit more detail at embodied carbon life cycle stages, what we call cradle to gate emissions. So from the very extraction to transportation to the factory to manufacturing. So it's cradle to manufacturer gate, essentially. And this is everything that the manufacturer really has control over for the most part. And these impacts are disclosed in what are known as environmental product declarations, or EPDs. So these are generally manufacturer-sponsored documents that state the environmental impacts of their product, including embodied carbon. Next, the product is transported, used with construction equipment, and replaced throughout its life. There's emissions associated with that, as well as any end-of-life processes, either landfilling, recycling. All of those things have associated carbon emissions. And so that entire life cycle stage is known as cradle to grave. And when we're trying to quantify this on a project level, we use an approach known as whole building life cycle assessment, or LCA. And there we're looking to really quantify this on a full life basis, on a cradle to grave basis. When looking at these life cycle stages, they're actually not created equal in terms of magnitude. This is a generalization, but generally what we've seen is that the significant bulk of emissions, almost 90%, are in that cradle to gate stage, the stage from extraction to manufacturing. So the manufacturer really has a lot of input into the emissions here. Something to note is that transportation to site is not very significant. On average, we're seeing 3 to 5%, and this is actually contrary to a lot of other paradigms in the green building movement, where you're looking at sourcing from nearby. While there are other benefits from a carbon perspective, it's actually better to source from further away if that product is manufactured in a lower carbon way than close by, and if it's manufactured on a dirtier grid or using coal. So really, the takeaway with this is that each situation needs to be evaluated, and that comparison needs to be made. So looking at a high-level overview of our process and what the recommended process is for evaluating embodied carbon, what takes the most time is understanding the quantities of your product. So we use everything from BIM models, cost estimates, to the drawings to ascertain the quantity of the material in the project. Once we have that, we use whole building LCA software to map environmental impact data to those products. So what we're doing there, I mentioned the EPDs, that's a type of environmental impact data. We're trying to represent those building materials with the best available data. So ideally we have, product specific EPDs, but occasionally you don't have that. So you have to use either similar EPDs, generic data, etc. So, the software puts that all together. We put together a number of other assumptions for, things like transportation, replacement during the building's life, the full lifespan of the building, and then we're able to get a whole embodied carbon number. And so that gives us, we can do a few things with that. That gives us, the top offenders, the top 10, which Andres will go in with a few examples. That'll give us some hot spots. We can really use that to to understand where the embodied carbon is and make recommendations and make changes to hopefully reduce the embodied carbon of the project. I'll quickly touch on a few of the leading tools that we see available out there. So one-click LCA, it's primarily a paid tool, but we found it as being one of the most leading tools out there. It has probably the best database that exists, so we really recommend that one. You may have heard of EC3, the Embodied Carbon in Construction Calculator. It's gotten a lot of support from a lot of big names, and this is really a database, a totally free database of building material carbon data. And the parent organization of EC3, Building Transparency, actually recently acquired another leading LCA tool known as Tally. And my understanding is they're going to combine forces there to really make it a cohesive, leading, and I think free tool. So a lot of interesting development there. And structurally specific, we really like to use Beacon. It's a totally free open source tool that works really well with structural BIM models, and quickly understanding the embodied carbon right there in the model. All right, and with that, Andres will take it away.
Thanks, Boris. I'm going to follow up that introduction into embodied carbon, really diving into why the structure matters by showcasing a couple of case studies of projects we've worked on and for which we've devised reduction strategies. Look into those strategies a little bit more in detail. Evaluate some of the material optimization that we recommend in the projects and where we're seeing the biggest hotspots of embodied carbon being reduced. And then afterwards, I will jump into the SE 2050 commitment. But before that, let me talk to you about why the structure matters and how the structural engineers can play a big role in tackling embodied carbon. First off, I'm gonna talk about Moffett Point. It's an office building in California. And really what I wanna emphasize here is demonstrate for this core and shell project, how the structure and the foundation, something that a firm like Miyamoto would be responsible for designing, makes up 80% of the total embodied carbon for this project. And then seeing the stacked bar chart on the left, we are showcasing the top 10 hotspots for this project specifically. And something to emphasize here is that 95% of the embodied carbon falls within these 10 categories. And our typical top 4 comes to concrete, steel, rebar, and the metal deck. So again, to emphasize how the impact that the structure can have and the different materials that make up the structure. That way we can have hone in and focus on these specific materials in trying to find either alternative solutions, ways to optimize the material, and therefore reduce the embodied carbon footprint of the building. For this project specifically, we calculated the baseline embodied carbon and put together a set of strategies that ended up reducing the embodied carbon by 35%. These strategies meant no design alterations at all. It was just a focus on material optimization and procuring low carbon materials. And these were implemented to less than 5% cost premiums. The 3 strategies specific to Moffett Point that we would like to point out is we called out higher cement replacement in concrete, so supplement and cementitious materials, so SCMs, ranging between 30 and 55%. And we also focused on the procurement of steel, for structural steel, looking for high recycled content and ideally produced in an electric arc furnace. Similar for rebar, the highest recycled content possible from a low carbon electric arc furnace and ideally from a green grid. I will get into the specifics of these strategies when I talk about material optimization. Kind of focusing on tying to Moffett Point specifically, how I mentioned the structure ends up making up 80% of the embodied carbon. So one of the strategies to keep in mind, and this might be the most interesting to the crowd today, is how how we can work on reducing the structure. So for this project in San Francisco, what they looked at is reducing the overall weight of the structure by addressing, a more creative solution to lateral forces. So here they've installed 32 viscous dampers, allowing the building to sway, in addition to transfer trusses at the base of the building, as well as in between levels 39 and 40, redirecting the loads to the mega columns. This, more creative solution managed or resulted in approximately 3,000 tons of steel saving. So that's not only a cost benefit to the client, but also, we're reducing we're seeing a 20% reduction in embodied carbon versus the alternative, which would have been a stiffer and heavier building with maybe a heavy damper at the top, which not only results in higher embodied carbon, but you're also sacrificing valuable real estate of the building, at the penthouse level. So something to really point out is we're seeing structure is a huge component of the pie, and you as structural engineers have the ability of approach a problem and try to solve, kind of think of outside the box, that with an embodied carbon perspective in mind. Another strategy I want to talk about in relation to Muffet Point is mass timber. So although this project did not end up pursuing a mass timber structure, it was evaluated, and we did quantify the benefits in terms of embodied carbon, versus a conventional concrete or steel structure. So speaking specifically to this strategy is, just pointing out that different types of timber will have, different emissions, but also different capabilities of sequestering carbon. So one of the big conversations around sustainability and the green building industry now is, with relation to timber structures, is biogenic carbon. And what that is taking advantage of the carbon that the wood itself has stored throughout its lifetime, and sequestering it in the structure rather than, for a more typical building resulting in greater emissions. Something important to point out is that in order to really quantify and take advantage of the biogenic carbon, the sequestered carbon, is that the timber has to be sourced from sustainable forests, and there's different certifications, specifically around the US, that focus on this. And that's just LCA best practices. Really, we can quantify the benefits of going mass timber versus a more conventional construction method, but only if the timber was sustainably sourced, and you can guarantee that using the product in the building is preventing those emissions. But even in the scenario where timber may not be FSC certified, it's still a substantial reduction when compared to the emissions from concrete or steel. So the next slide shows that baseline and optimized scenario that I had discussed earlier, as well as what the reductions would have been had a mass timber project been pursued. Well, it was a hybrid steel and timber structure. And we're seeing a total of 47% reduction from baseline. And that's because of, the lesser emissions of the mass timber products themselves, whether it's the glulam elements or the CLT, but also in the reduced quantity of concrete that is required as the structure gets lighter. And then the final bar chart at the furthest to the right shows that if this timber was guaranteed to be sustainably sourced from an FSC of forest, and you could count on the stored carbon, the biogenic carbon, you would have seen an 82% reduction from baseline. A second case study I want to walk through circles more around the benefit of retrofitting existing structures and or using them. The greenest building is the building that has already been built. And that's a push that's trying to be made in the green building industry. And this project in Chicago kind of showcases where we evaluated the addition to this existing office space, and measured the embodied carbon of that, but we also quantified what the embodied carbon would have been had the site been completely cleared and equivalent sized building been constructed from scratch. And that's what that gray bar shows on the left, is by avoiding the demolition of the existing building, the project itself was able to not reduce those emissions, but really prevent those from ever being emitted. So for this mixed use development project, we quantified the carbon savings of reusing the structure, which came up to 2/3 of the emissions, and then recommended additional strategies similar to the ones I just walked through of procuring low carbon concrete and steel, resulting in an overall 81% reduction of what would have been a similar completely new construction of a similar size and type. Again, this is kind of focusing more on a strategy of reusing existing buildings, and I just kind of doing some research into it, wanted to point out two interesting projects that I came across, one in Louisville and the other one in North Carolina, where they're able, the design teams have been creative in finding ways of keeping as much of the original structure as possible, whether it's the shell, repurposing the wood from a building into a different use in the new structure, or converting a completely different type building into something else by keeping the main structure and maybe adding some elements. In the example of the High Point, North Carolina project, they kept the original kind of manufacturing mill columns, the enclosure, the floors, and they added kind of an atrium that connected both wings of the building with a new elevator, glass elevator core with a snake stair surrounding to be able to access both buildings. So it's just examples of how you can get creative and finding a use of the buildings that are already out there, therefore avoiding any unnecessary emissions. And then just to point out, kind of adding to the scope, these other two projects were focused on the core and shell of a building. So therefore resulting in the majority of the emissions in the structure and the foundation, and then of course the enclosure making up the rest. However, we also carried out this study for an office building and parking structure, where the interiors of the project were also quantified. And kind of what I want to emphasize here and identify is, even with the interior finishes and furniture being included in the scope of measuring the embodied carbon of a project, the structure itself is still 2/3 of the impact. So even when kind of zooming out and taking a more complete view of everything that goes into a project, we're still seeing the main emissions being, concrete, steel, the rebar, the metal decks. Other components start playing into the mix, but it's still 2/3 of the impact. So it highlights the importance of focusing on reduction strategies that address the structure of the project itself. Which takes me to kind of discuss these high impact materials and optimization strategies that we recommend. So diving in first into concrete, although cement represents a small volume of the entire concrete mix, it contributes to nearly 95% of the embodied carbon per cubic yard of concrete mix. And overall, globally, it represents, cement production itself is responsible for 8% of the emissions. So we know that we won't be able to get rid of cement in the industry. Concrete's still going to be used, but there are ways that we can make more efficient use of the cement and replace it where possible. So we're seeing that you can achieve a 10 to 50% carbon reduction by some percentage of supplementary cementitious materials, be it slag, fly ash, glass pozzolan, typically ranging in the 20 to 40%, some projects even going up to 50. And then some concrete suppliers are diving into, evaluating how the mix would perform if we go even beyond that threshold. And then secondary strategies is, lesser carbon reductions, but still significant, is considering using other types of cement like type 1L, or breaking technologies like carbon cure that inject already emitted carbon dioxide into a mix, therefore keeping the same strength requirements while reducing the cement content of a project. And so sequestering carbon as an aggregate or recycled aggregates are also being explored, but these are more secondary strategies that we recommend behind, the big problem being cement itself is, the less cement you can use, the better. Going into steel, I think what is important to point out and where engineers can have maybe an impact is in specifying where the steel is coming from in the general notes language and the specs language, is understanding the two ways that steel is produced. So, most common basic oxygen furnace. The problem is it relies on fossil fuels to be powered. So although it makes up the majority of global steel production, it therefore is the reason why we're seeing high emissions from this manufacturing process. And it is typically used for HSS shapes as well as metal deck. And then on the other hand, you have an electric arc furnace. In the United States, it represents 70% of the US steel production. So the US is definitely ahead of the global average of the way that steel is being manufactured. And the benefits here is that you can achieve higher recycled content in the steel, and that it relies on the electric grid. So as the electric grid gets greener, Boris brought it up earlier, it results in even greater embodied carbon reduction. And typical sections that are manufacturing here is, angles, channels, wide flange beams, rebar. So here's a big, in simply making sure of specifying where your steel is coming from, you can have a large impact in the embodied carbon. And these are, the low hanging fruit that can easily be achieved just in ensuring these conversations are happening early in the design stage and before procurement. I'm going to dive into SE 2050. I know we've left some time for questions at the end, so if everyone's okay with that, I'll just continue and leave an open Q&A at the end, unless anyone has any pressing or immediate concerns with what's been discussed so far. If not, I will dive into SE 2050 commitment. So the SE 2050 commitment was publicly launched in November of last year. So it's very new, but in just these past couple of months, a lot of structural engineering firms have signed up. And the mission of this commitment is to really, the architecture industry has their 2030 challenge, and they've made a focus really on the architectural side to address embodied carbon and implement strategies to reduce the carbon footprint of the built environment. And it feels, or the structural engineering industry kind of felt we were kind of attaching to the AIA 2030, but we didn't have any guidelines or commitment ourselves to really guide the process. So it was kind of it was brought together by the Structural Engineering Institute with a lot of support from the Institute of Structural Engineers in the UK, the Carbon Leadership Forum, and what came up is this commitment of SE 2050. Again, it was published just at the end of last year, but it got support from the UK Institute of Structural Engineers after they declared a climate emergency in 2019 and as a reason to address embodied carbon in the built environment, as well as from the SEI Board of Governors who formalized it as a program in early 2020. So what SE 2050 is, basically it's a call to action. It's taking on huge momentum. A lot of firms are signing up, and really the purpose or how it can support the signatory firms is it can help this journey of setting targets, tracking progress, and really what's important is the data sharing that it will enable in creating better benchmarks. The more data that's available, the better the data quality will be. and to really drive that process forward of identifying where improvements can be made. It will also provide access to tools and resources for firms looking to achieve net zero embodied carbon structural systems by 2050, and whether that's through design improvements and optimization, which I touched on briefly earlier. There's also the contribution of greening the electricity grid, how the materials are produced, and carbon offset. So that's kind of the roadmap to achieving that net zero by 2050, and SE 2050 can lead to that. And I've included this analysis, that the kind of preliminary case study that they carried out, which the idea is to create these diagrams to educate and provide a range of values for typical analyzed bays for practicing structural engineers, to understand the different intensities of framing schemes considered typical. And the idea is, as more data gets put behind this, this will only get better. Just to point out, this specific diagram here to the right, it only included horizontal framing for a typical interior bay. So columns and other elements like lateral forces or foundations are not included, but it still gives a good idea of how these different framing or structural systems compare. And what does it mean for a firm that makes this commitment with SE 2050? There's more to it, but it can be summarized in 3 main points. It requires a commitment letter from firm leadership, specifying that the firm is committing to taking action in setting targets and tracking progress. It requires an embodied carbon action plan within 6 months of joining, and then to be revised annually, and then to submit data to the commitment for the data tracking purposes. And a little bit more into kind of what this means is by providing data, you're helping build a more robust database to inform those benchmarks and targets that are going to be set for the industry and improved as the process moves along. And they're currently launching this beta database of in order to reduce that data variability. And I've just pointed out there some of the things they would typically ask the structural engineer to input, whether it's a brief description of the structural system, of the project itself, and then for whoever's carrying out an LCA, a life cycle assessment on it, is understanding which tools were used, whether biogenic carbon was included or excluded, and the results as well. And this is all to build this embodied carbon intensity that will be shared between the firms and the commitment, and then also to create those benchmarks and targets for the industry. And here, really, the objective is education, reporting, reduction, and advocacy, with the intention of building a culture of change. And just to point out, I mentioned it was just launched in November of last year, so it's been 8 months since the launch, and they've already managed 47 firms to be officially on board. And I heard recently that 3 more signed up in the last 2 weeks. They're just formalizing, the requirements and documentation that I just touched on. So this goes to show there's huge momentum, and it could really help that collaboration in the industry. And to wrap up, diving into some of the key takeaways of this embodied carbon introduction, why the structure matters, and kind of what the structural engineering industry is doing with SE 2050. I want to touch of why it's relevant to all of you guys, right? So why as a structural engineer, why should I care about this? What can I do differently? And it's again to emphasize the big portion of the pie that structure and foundations represent, and the high carbon intensity of the materials that we are typically using in construction. With that in mind, I consider structural engineers to have the key to embodied carbon reduction, as we are in charge of those, the design and what materials end up being used in a project. And so, design optimization can really go a long way. Potential strategies, performance-based design, optimized utilization. There was a study showing how the utilization ratio is more rationalized, seeing in that top chart at the top right, and then how maybe the industry should reflect upon our assumptions around optimization of structural members, and kind of being willing to just evaluate things more on a performance-based level, to challenge the business as usual process of designing a structure. Other ideas would be lower carbon materials that are already available for medium or large scale residential and commercial projects, whether that's specifying less cement. Mixes are appropriate for different usages in the structure, considering maybe longer curing times. Specifying in your notes maybe max global warming potential of a concrete mix per cubic yard instead of a maximum cement replacement content. Requesting EPDs from the concrete suppliers. In the case of maybe sometimes emphasizing leaving the structure as the finish itself, that would address maybe more of the interior scope of embodied carbon. But I think there's a lot of, specifically to concrete and timber, of having the structure itself also be the architecture of the building. And lastly, designing for deconstruction and circularity. So knowing what will happen to this building at the end of its lifetime and seeing where it can go from there. This chart I took from Thornton Tomasetti. I'm not going to get into detail of each one of them, but it's just a good visual to showcase how different framing alternatives have a high variability of embodied carbon. And ideally, like, this visual challenge leads us to challenge our typical assumptions, or consider discussing different structural framing systems early in the design, whether it's questioning which materials are being used, or spans or base spacings. Are those do they need to be that wide? The bottom two circles there show the difference of just going from a 3-meter span to a 4.5-meter span. Considering reduced loads, what other structural systems should be considering. So really, what some would call structural optioneering of early in the design, and seeing where you can go in terms of the carbon footprint of the building. And how structural engineers can help is, again, advocate for sustainable design, making design decisions based on embodied carbon. Following something like SE 2050, where a firm commits to tracking and reductions over the next couple of years, which is, as Boris mentioned, the time value of carbon. And there was a quote there at one of the earlier slides, where we can't just wait till these emerging technologies just take care of offsetting emissions, but rather take a more proactive role. So whether it's through, I point out here specifications as an example of something that is low-hanging fruit that can be addressed and very easily, in just maybe changing some of the language, and how that can really lead to major reductions. I took the chart from the right from the Institute of Structural Engineers in the UK, and how they describe it is there's like a now problem and a next problem. The now problem being probably the next 10 years, and it's merely a cultural shift in design of what already exists, and what can happen now with different strategies, and you can see it opens up more. The potential opens up the more collaboration there is. And then the next phase relies more on technologies which are either currently being developed or under research, or where scaling up of existing technologies is necessary. And they consider it's imperative to boost this type of research and development and innovation in order to, in 10 years' time, when we exhaust the gains and reductions that we can take advantage of in the now phase, and what we're prepared to do now, as of today, to make sure we don't lose pace and have new approaches to continue making carbon reductions year over year in the coming decades. I found it pretty funny that in their outcome 2 box, they say that we should be aiming for before 2050 because it's the building industry and we know we will be late. So it's just emphasizing the urgency of how the earlier this carbon is addressed, the better off we will be. And that is all from us. We're leaving some time for questions. Thanks everyone for your time, for joining us. And I hope this was informing and interesting to everyone.
Yeah, thanks, Andreas and Boris. We really appreciate it. Does anybody have any questions? I have one to start with. You mentioned a max global warming criteria for concrete mix designs. Is that readily available historically in concrete mix designs? Have you seen that? I hadn't heard of it. I hadn't seen it, so I'm curious about it because I'm sure it's going to come up.
I can answer that one. What's great for that specific topic is there's a few policies we can look at. The leading policy is the Marin County Low Carbon Concrete Code, which was released in 2019. And so that was really collaboration with a number of kind of top players to figure what those limits should be. And so they have specific limits based on the concrete strength. And what I think is really great, they have GWP limits, which you can get by only by really having an EPD, but not every concrete mix has an EPD. So for those that don't have that, they have maximum cement content by strength. And so we've actually worked with some clients to implement that on their own projects, through their specs and general notes. And a lot of other municipalities are really looking at Marin County as kind of a case study of what they could implement in some larger cities.
Makes sense. Yeah, we've seen that. Okay, thank you.
And this is Kid. I have a question. Can you hear me?
Yeah.
Yes.
Yeah. All right. That was a nice presentation, Andres. So we've been using the so-called seismic dampers for, 20 years. And one thing we noticed for the last 10 years is when you use the system, you can reduce the steel tonnage by about around 20 to 25%. So we never actually talk about carbon footprint reduction, based on the using the technology. Actually, that many cases cost less because of steel saving quite a bit, But somewhat we had a difficult time to convince the clients over the years, So this carbon footprint reduction components, especially steel construction, for 25% reduction sounds like a big deal, isn't it?
Mm-hmm.
So do you test it, like how public perceives it? I mean, investment communities and stuff like that, do they really say ticket, Because we talked about like resiliency, we talked about the probability of collapse reductions, stuff like that, But this actually immediately they can have an impact. But see, when you do like resiliency engineering, only benefits come when a big earthquake hits, right? So they don't see earthquake ever happens. It's kind of difficult to sell, right? But carbon footprint thing is going to be immediate, right on the spot. When built things, you can have a 25% reduction. And it sounds like a huge number. It seems like be able to convince the investment community. What's your thoughts?
I can speak from the owner's perspective actually on that. Hey, Kit. So Rebecca Cully here. I'm responsible for environmental design at Apple Inc. And I guess I'll answer that question from our perspective from two different sides. So the first side is just the value proposition. So Apple has publicly stated that we are aligning ourselves to the IPCC and the Paris Accord. The Paris Accord, of course, is the documentation and the program that seeks to hold the core temperature of the planet to no more than 1.5 degrees Celsius by 2050. Publicly, we have stated that we are intending to achieve net carbon or carbon neutral by FY 2030. And Lisa Jackson, who is our Senior Vice President of Environment at Apple, has stated that we're going to do that by optimizing Apple's value chain, or rather the carbon associated with our value chain, by 75% from our 2015 baseline year. And so what that means for us is that across the board, be it our supply chain on our product side, the operation or the embodied carbon associated with our buildings, transportation, to include the operation of the devices that you all use of ours, we are intending to pull 75% of the carbon associated with our products and our value chain out of our pipeline entirely, which basically means that from the building perspective side, we have to engage with our structural engineers in order to be able to achieve those really audacious targets that are aligned not only with our values as an organization, but also, of course, the IPCC and the larger UN kind of that global intent to achieve that target. So that's kind of the value side of it. But there's also a financial side of it, because more and more and more, we're starting to see this notion of carbon taxation become a much bigger deal. And organizations like Apple, who would be beholden to some of these really significant financial risks, need to understand where that potential risk exists. We've seen it in Australia. We've seen it currently in Spain and some of our other locations throughout Europe. But our carbon tax exposure is not insignificant at the end of the day. So working with those structural engineering teams to pull the carbon out of our buildings at the onset is the best resource or the best way that we can think about reducing our long-term risk associated with carbon taxation. So I think for those of us that are playing significantly in this space, or that are publicly disclosing what we call ESG metrics, or environment and social governance metrics, so we're talking all of the companies that are signatory to the Carbon Disclosure Project, so on and so forth, are very keen on making sure that our buildings are aligned with Paris.
Well, Rebecca, sounds like Apple Corporation needs us to put all the seismic dampers to all your seismically active stores globally.
That's what I heard too.
Seems like that's a given, like a requirement, actually required. It's not like options, remember. So that's good to hear. What about the you guys talk about like a minimum building code or not kind of things, because in a disaster scene, obviously if you design per code, save lives, but not be able to save buildings, so therefore you have to construct. For example, New Zealand, out of 2,400 buildings in Christchurch after 2011 earthquake, 2,200, there was concrete structures, they completely disappeared, they're gone to that landfill, right? So they are reconstructing right now as we speak. It'll take 10, 20 years. But it's a lot of buildings to build, made of concrete and steel. So carbon footprint caused by the disaster is humongous. Do you guys talk about that? So it's because there's a ways not to take the buildings down. I think dampers one other options. There's some many different ways to create a higher resiliency per se. That U.S. Resilience Council doing kind of similar kind of things essentially. Any of that term become the carbon footprint discussions ever yet? It should.
Yeah, I agree with you. It definitely should. And I think all these things of, the climate emergency and resiliency and the carbon footprint of the built environment are very much intertwined. Well, I'll let Boris speak afterwards in case he has encountered this. I've, again, just transitioned to this like sustainability side of the industry recently. But kind of using that project I used as an example, the Fremont project in San Francisco with the dampers. They were able to, and I'll point out we were not involved in that project, but I'm just using it as an example because they went that step further and look at, okay, what's going to happen after that, the event we're designing for happens, right? So the building codes will mandate for the building to be able to be safely evacuated and, minimize damage. But they carried out this design through a more rigorous testing of, the big one in the Bay Area. I think they went up to an 8 magnitude earthquake, and they demonstrated that the building could resume operations the following day. And the takeaway from a carbon perspective in that is, okay, I showed that core shell and interiors project where, the interiors also represent a big portion of or a significant portion of the impact, and maybe not taking that step of the Christchurch earthquake which devastated the city, but maybe you have an earthquake which won't knock the buildings down, but maybe you have a bunch of repairs to do on the insides, and all that replacement of interior partitions, walls, all the finishes, all of that still kind of bites into that let's call it carbon budget that you may have for your project. So I think this issue of bringing resiliency and kind of how what the before and after of the structure is, after a big event, goes, yes, mainly obviously the safety of the building, and then focusing on the impact of the structure itself, but it also has a huge impact on the interiors, because that's what we more typically see. You're designing for, safe evacuation of everyone, minimal damage, but even that the replacement of that minimal damage is, again, all those TI scope of work will result in embodied carbon. So I agree with you. I think these things are definitely intertwined, and I guess I'll let Boris talk to see if this has come up in other conversations.
No, Kit, that's a really great observation. And I think the industry needs to connect those two more. I recently heard a talk about buildings that are not up to seismic code as stranded carbon assets, because if an earthquake hits, that's going to be all that carbon that was really wasted and will have to be replaced, like in Christchurch. So I do think that's a really great observation and the direction the industry needs to go.
Like we go over the world to actually define the debris. Like for example, U.S. government sent us to say Costa Rica and San Jose. So we see that what type of risk exists, has a either hurricane or earthquake, and we actually calculate out how much debris comes out. 5 million cubic meters of concrete in that kind of stuff. So from there, I feel it's fairly easy to calculate out what's the carbon emissions from this particular concrete, right? Because they have to reconstruct it essentially the same way. So on top of it, because we've been talking about metrics like the concrete debris or fatalities and stuff like that. On top of that, I guess we can talk about carbon emission caused by this particular
Definitely.
event. So that makes a difference if the city is resilient or not. If city is not resilient, the potential carbon emission is much higher because of that reconstruction.
Yeah, I would also say too, from the Apple perspective, we won't even entertain a new design without understanding carbon footprint.
So do you have like a easy spreadsheet I can use to figure out those things? Like 1 million cubic meter of concrete.
Yeah, I would say that the Beacon tool, I can send a link here, is really good, free, and loads right into Revit. So I'd say that's a good place to start. I'll share that.
Yeah, Beacon is a good tool in that it plugs in, it's a plugin in Revit. So you have all your structural elements modeled there with, the corresponding material properties, and it'll do like a really quick output of, okay, you have X amount of concrete or steel, and, you specify these strengths, and it will give you a carbon value for those metrics. So it gives you a good understanding early on, kind of where you at. And I think as maybe the industry moves towards setting limits of, how high carbon emissions can be in a building, it's a good tool, a good resource to have during the design process. You don't need to, go into any different software or change anything else. And the other one would be, Boris mentioned the EC3 tool. That could give you more of an idea of when you're considering, different mixes or different strengths, different curing times. That has a very robust database that is open to the public, where you can see maybe what the carbon reduction would be if you specified, 56-day strength versus 28, or whether you use the higher replacement content percentage. We can also send a link to that one if you have some free time from designing and want to poke around.
Cool. Anyone else have some questions?
Yeah, good stuff.
Actually, I do. Talking about low carbon materials, I wanted to know if you guys can provide any feedback on Blue Planet aggregate. We've been seeing that in a little bit of our research, and I was just curious if you have any feedback on that.
Yeah, the promise of Blue Planet, which those of you that don't know, they are looking to precipitate aggregate from CO2, from CO2 in the atmosphere. So using might be a chemical or biological process to actually create, aggregate minerals from CO2, sequestering that and using that in concrete mixes. So as you know, aggregate is the largest volume in a concrete mix. So there's a lot of theoretical potential for sequestration. We've seen Blue Planet implemented on one pilot project, and we've been told that it's kind of in the works to become commercially available, but we haven't seen that scaling up come to fruition yet. So we are also, we're really excited about the potential, but I don't think it's there yet.
And what about type 1L cement? I thought that was only being used in Seattle or Portland. Has Caltrans approved it yet?
Yeah, that's what a lot of, in California, that's what's being waited on, Caltrans approval. There are, because basically the concrete, the ready mix suppliers will only have one type of cement. That's what they always tell us. And then unless, Caltrans approves it, they don't want to have another pile of cement. So it's things like that that are kind of holding us back. But, Cal Portland, the cement manufacturer, has a kind of a hybrid mix available called Advancement. And there's some movement in that direction. And, hopefully Caltrans will have it approved shortly.
Anything else, Jeff?
Yeah, it's great discussion. I really appreciate you guys helping us out and sharing all the knowledge you have.
Wonderful.
A lot of this is new to many of us. So, although we live this world, so we're definitely interested in everything you said. Rebecca, thanks for joining. We need to go hiking again.
Yes, let's do it. When's the next Miyamoto death hike, you guys?
4 or 5 years, probably. I don't know. Well, Kit's around more, so it should be easier to plan.
Yeah. 2 weeks. Week about August 10th.
Okay.
Yeah.
Well, pleasure to see everyone again. Really appreciate the time and the attention to such an important subject. Thanks for
Oh yes, this is actually super critical. I think that this kind of information really help us convince our clients, to act on it.
Yeah, huge.
And one of the tools. That's just fantastic. We're definitely going to incorporate into our whole statement what information system.
Amazing.
Yeah.
So
Sure.
thanks so much for everybody's time. Appreciate it.
Yeah, thanks everybody.
Thanks so
Thanks,
much, guys.
everyone.